Let's see if we can answer this question up here. What is the sun responsible for in our solar system? You guys had this yesterday, and concept number 1, solar flares versus CMEs, that was your bell work. There's a video that answers that after you press submit on your bell work, and it looks something like this. We're not going to watch it on this video, but you can watch it on bell work. There's a test next week. I don't know the exact date, but I want you to be ready. There will be a test. You may be asking, if you can't see through the photosphere, if you cannot see inside of the sun, how do we know what's happening in there? The first answer is math. We can mathematically represent what's happening to atoms and subatomic particles when they reach certain temperatures. We can mathematically determine what those temperatures would be. But how do we actually make measurements from inside the sun? We use what's called helioseismology. Helio means the sun. Seismology here on Earth is earthquakes. It's studying earthquakes, figuring out how earthquakes happen, why they happen, trying to predict if they're going to happen. That's seismology. It's measuring the waves as they travel through a celestial body. One of the first things that Neil and Buzz put on the moon was a seismometer to see if there's any sort of seismic activity up on the moon. Now you might think, if the sun's not solid, how do you have seismic waves, earthquake waves going through the sun? The answer is that the sun actually vibrates up and down. We know that those columns of gas rise up through convection, and that's what's causing the granulations on the sun. We actually have detectors that are sensitive enough to be able to determine, as they rise up, if they're coming towards us, or as they sink down, if that material is moving away from us. And we use the Doppler effect, which we're going to get to quite a bit later this year. We can actually measure how fast they're moving up, how fast they're moving down, and when that changes, that means there is a wave traveling through the sun. We can see a wave on one side of the sun, measure the time that it takes to go to the other side of the sun. Different densities will have different densities are going to have different speeds associated with it, and by studying those waves on the surface of the sun, we can actually determine what happens inside of the sun. One of the incredible things about this vibration of the surface of the sun going up and down is that they can turn those vibrations into sound. Sound waves is nothing more than vibrations causing ripples in some medium, whether it's air or water or a solid. And those vibrations would be going much too slow for our ears to hear. What NASA has been able to do is actually take those vibrations and increase their frequency up into the audible range so that human ears can hear it. They've turned the oscillations of the surface of the sun into a sound. So we can actually listen to the sun. That's what this background noise that you've been hearing is. I'll let you listen to it a little bit better for a second. Here's a little video explaining that a little bit better.
The sun makes sounds, but they're not really sunny sounds. They're not happy sounds. They're kind of low, ominous roars that gurgle along. The sun makes sounds because there are a bunch of gases going up and down through a process called convection. So they're sending pressure waves through the ball of gas that is the sun, and it kind of rings like a bell.
Unlike a bell, the sun rings with 10 million different tones at once. We detect them from the tiny bulges from the pressure waves on the sun's surface. Solar satellites measure the height of the bulges with exquisite accuracy. Apart from sound, they also produce science.
So using these sounds from the sun that we can observe, we can actually tell very detailed things about the interior structure of our star. For example, one of the amazing things that we can tell is when there's a sunspot group on the other side of the star, even before it comes around the limb and we're able to see it with our optical telescopes.
You guys wrote down a bunch of information about the different layers of the sun. Really quick, let's go over the top 3 layers from the photosphere out. So the photosphere is where we get helioseismology. It's where sunspots happen, it's where CMEs happen, it's where solar flares happen. Most of the stuff that we see happens on the photosphere. And then you have the chromosphere, which is kind of like the sun's atmosphere. It would be similar to our atmosphere on Earth. It's just above the surface of the sun. And then you get to the corona. And the corona actually turns into the solar wind and extends all the way out to the edge of the solar system. Those prominences and CMEs and solar flares that happen on the photosphere extend out into the corona, and a lot of that material actually ends up in the corona. You should already have this written down, but just in case you don't, the photosphere for the sun is about 5,800 degrees. When we say what is the surface of the sun's temperature, it's about 5,800 degrees Kelvin. The chromosphere, or the sun's atmosphere, is about 1,000 kilometers thick. It is much thicker than our atmosphere, much taller than our atmosphere, and it has a temperature all the way up to about 10,000 degrees, almost double the surface of the sun. Then you go out to the corona. The corona is ionized particles that are streaming out from the sun. It's millions of kilometers thick, and its temperature is millions of degrees, about 1 to 2 million degrees. And you might think, if the surface is only 6,000 degrees, why is it millions of degrees farther away from the sun? That is one of the biggest mysteries of the sun. As you move out from the surface, you get hotter, and then much, much hotter. About 6,000 degrees, about 10,000 degrees, and a couple million degrees. Why? We're not sure. We think maybe it has to do with a couple things. Number one, there are these things that are called mini flares. There are millions of them happening all over the surface of the sun every single second. And those mini flares are shooting a ton of energy up into the corona and the chromosphere, possibly heating them up. The second could possibly be something to do with the magnetic field lines. If those magnetic fields are getting tangled, they may somehow translate some of that energy into heat energy, thus heating up the corona and chromosphere. And the final hypothesis of how it gets hotter as you move out actually has to do with sound waves. We know that the surface of the sun has a lot of moving material. Things are rising up, things are sinking down. If you've ever stood in front of a speaker as it is very loud, you can actually feel the sound waves. The sound causes the air as it travels to your body to compress and refract and compress. It moves air particles. Well, if the surface of the sun is also moving back and forth, it's technically creating sound. And as those sound waves travel outwards from the sun, it's causing those particles that are farther away to vibrate. The sound is so loud that it's causing those particles to vibrate so fast that the temperature is going up. These are all hypotheses. We are still unsure of exactly why it's hotter the farther out you go. And until we can send a probe into the sun, which I'm not sure how that will happen, but as of now, it's a big mystery. A couple pictures, the photosphere, the surface of the sun. This is where the sun becomes transparent. If you are some light, if you're a photon inside or underneath the photosphere, then you are constantly going to be absorbed and then re-emitted, absorbed and re-emitted. As light, you cannot travel in a straight line. Once you get to the photosphere, the density changes enough that light can now travel in a straight line, and light will then travel to Earth. That's why we can see the light as it comes out of the photosphere. Not because that's where the light is created, but that's where light is now not constantly being absorbed by atoms inside of the sun. The chromosphere is this kind of orange layer. It's the atmosphere. It's only visible during a solar eclipse, or if you're using a special attachment on a camera where you put a little filter on your camera that actually blocks the disk of the sun and acts as an artificial eclipse. And then you have the outermost layer, which is the corona. Oh, wrong picture. The corona. Again, only visible during an eclipse, and you can see that it travels millions and millions and millions of miles out from the surface of the sun, And most of this material just continues on, and we refer to that as the solar wind. Why are there no pictures inside of the sun? Well, because light can't travel in a straight line. We can't send a camera there, it's too hot. And light that is inside of the sun is going to immediately be absorbed by something. Even if we could send a camera in there, it would be like putting a camera inside of a big pool filled with milk. It would be completely black because light can't travel more than a very small little distance before it's immediately absorbed by something else. Sunspots. We've talked about them a little bit, but I want to go over them a little bit more. To me, sunspots look very much like this. What is this? Some of you may recognize it. That is the Eye of Sauron from Lord of the Rings. But whenever I see a sunspot, that's immediately what pops into my head. So today's question, what information about the sun can we gather from sunspots? From counting them, from measuring them, what can we learn about the sun? Galileo was the first person to actually see sunspots. He's the first person that was smart enough to take a telescope and point it up at the sky. Before that, they were always used to look at distant things on land. Now, he did not take that telescope and put it to his eye and look at the sun. He would have ruined his retina, he would have gone blind. Instead, what he did is he pointed the telescope at the sun and then projected that onto a wall. And when he projected it onto the wall, he put a piece of paper up against that wall and traced what was being projected through that telescope. This is an actual page from his notebook where you can see that he's traced the circle of the sun over and over again as time goes on. And he recorded or drew all of the sunspots that he saw. And you can see that there's a bunch of them, and then there gets to be less and less of them, and then there's a bunch of them, and then there's less and less of them. So the amount of sunspots changes week to week, month to month, year to year. He was the first person to actually figure out that the sun has a cycle of sunspots. He's also the first person to realize that the sun, the surface of the sun, changes over time. This is an interesting photo. It's actually a number of photos put together. Each one of these suns is a combination for an entire year. So what they did is they counted all the sunspots that happened during an entire year, and they put them together in this sun here. And then they did the same for every sunspot that happened, put them on that sun. Then they did the same for this one. And so this is the composite for an entire year. That's the next year, and you can see that over time, you go from not a lot of sunspots to there's virtually nowhere on the surface of the sun that didn't have a sunspot, back to hardly any sunspots. This is the sunspot cycle, where you go from a hardly any to a whole bunch, back to hardly any. You plot these out on a graph, and you can see that roughly every 11 years, you get a whole bunch, hardly any. A whole bunch, hardly any, a whole bunch, hardly any. And the number that you get as the peak for each cycle is not consistent. So some peaks are going to have, that's 200. This peak had less than 80. But we do still see that there's a very repetitive 10 to 11 year cycle of a whole bunch of sunspots, not a lot, back to a whole bunch. So what exactly is a sunspot? A sunspot is a temporary dark spot that's on the surface of the sun that's caused by the crazy magnetism happening at the surface of the sun. That crazy magnetism is going to cause all of those convection currents bringing hot material up from the center of the sun to stop. They're going to turn off. And when they turn off, no new hot material is being brought up, and so what's at the surface starts to cool down. As it cools down, it appears darker. The temperature of a sunspot is about half that of the regular surface of the sun, between 3,000 and 4,000 degrees Kelvin, whereas the regular temperature is 5,800 to about 6,000 degrees Kelvin. Still very hot, but it's definitely visible as a dark spot on the surface of the sun. Sunspots actually have two poles. They have a north pole and a south pole, just like a magnet would. Sunspots, to me, actually look like they're alive. They look like they're living organisms, like an amoeba or something. They're going to appear, this is actually a time lapse of actual sunspots that are happening on the surface of the sun. They appear, they move, they expand, they contract, they merge together, they break apart, they change size, they change their shape, they change their position. They can get up to about 80,000 kilometers in diameter. The Earth is about 6,000. So they can be 7, 8 times bigger than planet Earth. As they move, they also go pretty fast, moving a couple hundred meters per second, which is faster than a bullet. So these are huge, huge phenomenon that are moving very, very fast. We've mentioned that sunspots happen because the intense magnetism slows down those convection currents and causes the material at the top to get a little bit cooler and therefore darker. On average, the magnetic field of the sun is about twice as strong as the magnetic field on planet Earth, if you just picked a random spot on the surface of the sun. However, at a sunspot, the magnetic field is about 1,000 times stronger than that. So about 2,000 times stronger than planet Earth. And because it is so incredibly strong, you can actually measure the magnetic field of the sun all the way out where Pluto orbits. The sun's magnetic field can be detected and measured throughout our entire solar system because it is so incredibly strong. Here's a little picture of the sun's magnetic field being all nice and neat. As the sun is spinning faster at the equator, slower at the poles, it starts to twist, and eventually it gets tied in knots. And all of these magnetic fields then kind of break apart. You have North Pole, South Pole, you have sunspots that start to happen, a bunch of messy knots that are all tangling together, and then it snaps back together, and you can see that the magnetic north used to be at the top, and now the magnetic north is down at the bottom. That's why the magnetic field of the sun switches after there's a whole bunch of sunspots. We call that the polarity cycle, meaning the North Pole is at the top, then it goes to the bottom, then at the top. And if it switches every 11 years, it takes 11 years to switch, 11 years to switch back. So the polarity cycle happens over a 22-year cycle. What do sunspots do? Well, first, they slow down convection, but because they're areas of such high magnetic intensity, almost always they're associated with solar flares and CMEs, of stuff being shot out of the sun that wouldn't otherwise normally be shot out of the sun. So a solar flare almost always is associated with a sunspot, and they've been measured at temperatures of 40 million degrees Kelvin. The center of the sun where fusion happens is only 15, so this is about 3 times hotter than the center of the sun. This is one of the reasons that they think that the magnetic field is one of the things contributing to the outer layers of the sun being hotter as you move away. We get those prominences or those coronal loops where if you look closely, you can see that this material is moving out of a solar flare, which is associated with a sunspot, and back into another solar flare or sunspot. Why does it look bright? Well, this is not visible light. This is actually in ultraviolet, and in ultraviolet, solar flares are much brighter than the rest of the surface of the sun. Finally, because of those crazy magnetic field lines, oftentimes material will get trapped up in that and get slingshotted out of the sun. You'll get a coronal mass ejection, and that can definitely affect us here on Earth. It causes the auroras, it causes satellites to malfunction or turn off, or maybe could possibly end civilization. How are they helpful? Well, sunspots are what allow us to measure the rotation of Earth. So if you watch a single sunspot as it travels across the surface of the sun, you can actually measure exactly how fast that area of the sun is rotating. And that's the only way that we have been able to measure how fast the sun is rotating at the equator versus at the poles, is by watching sunspots that happen at different places. As a reminder, at the poles, the sun takes about 25 days or so to go around once, and at the equator of the sun, it takes about 35 days. How do we know? We watch sunspots as they travel around on the surface of the sun. Let's take a look at sunspots in different wavelengths. Visible light, a sunspot is going to be much, much darker. However, when you change to infrared, still have a sunspot being much darker. Let's now go to ultraviolet, and the sunspot is now the bright area. And a lot of times you will see an ultraviolet photograph of something like a solar flare, and it looks very, very bright, even though it's coming out of a sunspot. Why does it look brighter? Because it's not in visible light, it's in ultraviolet, which is why if you go back to our solar flare, this is a sunspot right here, but that's taken in ultraviolet, so it looks brighter when in reality it's not. So this is 2020. One of the things that we would have done this year is a lab where you would have been in a group and your group would have been given some data. And as a group, you would have graphed the sunspot cycle. You would have been able to see all of the maximums and all of the minimums. You would have been able to calculate exactly what the time between the maximums is, so between the solar cycles. And this graph went from roughly 1700 to about 2015 or so. One of the follow-up questions actually asks for a prediction, what do you think would happen before 1700? What would this graph look like? Turns out that Galileo, back in the 1600s, discovered sunspots, and as soon as that discovery got out, everybody around the world was counting sunspots. So we have actually a pretty good idea of the sunspots that were happening in the 1600s and what that graph would have looked like. There it is. So here is the graph that you would have done in your lab down to about 1700. And in the 1600s, turns out that cycle stopped. And we don't know exactly why. Originally, people thought maybe they weren't very good at counting sunspots. But if you take a look, actually, no, counting sunspots is not that difficult. They had roughly the same technology here that they did over here. So for some reason, for about 80 years or so, 80 to 100 years, there was no sunspots. There was no sunspot cycle. And this is what's known as the Maunder minimum. The Maunder minimum is a mystery. We don't know why that happened. We know that it did because we have data, but we don't know why. I'm wondering if you guys know of anything else that happened back in this time period. So there is something that's called the Little Ice Age, where across the world, temperatures got colder. Winter lasted longer, the growing season was shorter, food production was interrupted, and there was famine all over the world, people were dying. It was pretty bad. And this, what's called Little Ice Age, coincided with the Maunder minimum. Is this absence of sunspots solely to blame for the Little Ice Age? We don't know. Maybe there was some other stuff going on. But we do know that they coincide. We also know that sunspots, with their increased solar activity, send out more energy into space. So when we have more sunspots on the surface of the sun is actually releasing more energy. And if all of a sudden we have no sunspots, the sun is releasing less energy. And it's not that hard to figure out that if the sun's releasing less energy, it's not going to heat the planet up as much.